morning? I didn't get my noise. Oh, that's right. I muted my noise in my. I was in a meeting earlier and things started playing sounds. It was a very boring meeting. I had to do emails and stuff during it, and then I send an email. It's like whoosh. Whole room of people. All right, very good. This is 48 ounces. You drink 48 ounces of this.
Yeah, well, actually, you're gonna, put some heavy sweetness in your kidney now.
I only have one kidney.
What?
No.
Did you say that?
Seriously?
I was born with only one.
Oh,
No.
But I didn't find out about it until I was like 25 or 26, something like that.
Seriously?
Yeah. No, dead serious.
You know,
I was having like some stomach pain, and I went to the doctor. It didn't go away for a couple weeks. They bringing me in for MRIs. They're injecting dyes into me and stuff like that. It turned out I have an absent left kidney. Nothing was going down there. All the pain ended up going away with one. I had took one thing of Gas X and an Advil. Never had pain again from it. But 2 weeks later, I find out I'm missing an organ.
I have a friend in the Houston. He go to the Chinese for a trip, and he literally got a food poisoning. He go to the hospital. I don't remember where he's going, but they took his kidney when they surgery.
Just took it out?
They drop it.
Yeah, I got to sell that.
this happens very. This is a normal thing back in India.
I know.
When he came back to the Houston, he feel weak. He go back to the hospital. The hospital say he lost his kidney, and he was like crying out. I just got a food poisoning. I go to the hospital. My surgery and they dropped my kidney.
Well, did they leave him with one kidney? Well, so you should be thankful. If the people were too greedy, they would have taken both.
I remember there was a news that said that people back in India, they sold their kidney to get an iPhone, which was then very costly.
Man, you want to get more for your kidney than that. There's an interesting movie. I can't remember the name of it, but it's kind of based on this. It's a little bit of a movie that's kind of in the future, where we have artificial organs. So if like somebody needs a liver, or they need a heart or something like that. So some company sells these artificial organs, and they're like crazy expensive. So when somebody, if they're going to die, they'll like, I need a heart or I need an organ, and they'll take out basically a mortgage on this like crazy expensive, organ. But then if they don't keep up with the payments, the people go out and recall it. So they'll yank the organ right back out, and the person they don't make it then. Yeah, I'm trying to think of the movie's actually pretty good. Yeah, I just don't remember the name of it. Some point, maybe the middle class will just pop into my head. But Repo Men, that's it. It was good. Okay, so did you guys do your C stuff in here? Or you did it on a command line or something like that? Did it use this guy?
Online GD.
So you didn't use JDoodle?
No, we used it. It's called onlinegdb.com.
Online G. That one?
Yeah.
Oh, was I using that in class last time?
Yeah.
Ah, perfect. I sometimes do smart things. All right. So let's go ahead, and we're supposed to fill up I think I gave you the code to fill up something with random numbers last time. All right. So was that in? Oh. Leave. Oh, this is the one I already used. Ah, perfect. All right. We're back. All right, so I went ahead, I created an array that has 50, enough memory to hold 50 integers. I went ahead and filled it up with 50 random numbers, and I just proved that it had 50 random numbers in it. Let me go ahead and run this real quick. There's my 50 random numbers. All right, so now we're supposed to write an insertion sort. So just for testing this, I'm going to go ahead and I'll show you a couple other things in C while we're doing this. I'm going to create a function down here. And this guy is going to be void print array. And this guy will take an integer pointer as a parameter. If we go off the history of these things, it also needs to take in an int size. Although technically with modern compilers, you can get the size of one of these structures. But I'll pass it these two things. So I'll pass it an integer array as well as the size of that array. And then I'm going to go ahead and I'm going to create a for loop. In I for I is equal to 0, I is less than size, I plus plus, and we'll say printf. %d \n, and we're going to print out the value that lives at memory address AR plus I times the size of an int.
What's the \n for do?
Carriage return.
Carriage return.
So actually it stands for line feed, but most modern things it's carriage return and line feed.
Could you do just printf and then quotations of something to print that?
Yeah, so I mean if I leave that off,
Yeah.
it'll just print all of them all on one line. It'll just compress them together. Or if I want to just put spaces.
So that /n new line.
Correct.
Oh, okay.
Yeah, so this actually might look cleaner if we write it this way. If I just do a final printf \n like that. And then up here, rather than call this, I just call my print array. And I'll pass it AR, and I'll pass it the size, which was 50. All right, now hopefully this gives me a error. Oh, how do I save in this thing? Oh, I got to hit save. Oh, it's Control S in this. I get it. All right, so I went ahead, created my array, filled it up with random numbers. Then I'm going to call my function print array because I'm going to want to call it multiple times so I can print it, sort it, then print it again. So I just wrote the function. And hopefully we get a warning here. Oh, we don't. Stupid modern compilers. All right, so yeah, I'm gonna show you what we would have gotten a warning from. Historically, in fact, I actually can probably show you from my command line. All right, so I just put the exact same code in that we had on the thing. I tried to compile it here, and notice it gave me a warning saying implicit declaration of function called print array. All right, and the reason for that, it's telling me to, if I'm using C99, the 1999 version of C, I'm trying to call a function in main here that it doesn't know about because I actually haven't defined it till later on here. All right, so this was a problem in the early days of C programming. So what people would do is they would do something called prototyping. So they would take just the header for their function. They would come up top here and they would prototype that. Wouldn't even have to give it the variable names, just the types it took in. So now they would prototype it like this. That way the compiler hit this and read in the symbols for this function called print array that takes in an integer pointer and an int. So that when we got here in main, it knew what we were talking about, even though that guy wasn't actually implemented until later on down here. All right, so this is called prototyping that function. And just to show you real quick, I'll just copy that code again. I'll go back out to my terminal. Oh, perfect. And now you see it's happy with it because I've prototyped that line. That makes sense? Now, what would start happening then, though, is as you wrote bigger and bigger programs that got more and more complex, and we're going to spend some time writing some stuff in C today. We're going to talk about how to represent sign numbers, two's complement, stuff like that. So we'll manipulate some more binary stuff in C because it's fun. But you can imagine for a large program, you'd have a whole bunch of prototypes up here at the top. So that's where header files came in. So what they would have you do, I assume I can create a new file, right? All right, so let's call this guy, we'll call it Mike.h. Okay, or actually, let's go myfuncs. Myfuncs.h for my functions. All right, I'll go ahead and do that. And I'm just gonna steal this prototype line from here. And instead of having it at the top in here, I'll put it into myfuncs. Just like that. All right, nothing special. And then I'll go back in here and I'll include. Now, whenever you have the little angle brackets here, you're using system libraries. If you do a double quote, and I have something called myfuncs dot, I did call it funcs, yep, myfuncs.h, like that. Now, I keep hitting the wrong thing to save. It's Control S on here, okay. Now I'm including the contents of myfuncs, which is effectively my prototypes. That make sense? And what became nice for this is you can now organize your various functions into different header files. You could actually implement them in the header file if you really wanted to. Most people don't, but you could. All right? At least most people don't for individuals. They do if they're using a third-party library. Then the things are implemented in there. But punchline for us is myfuncs gives me a nice kind of concise, assuming I had 40 different functions in here. If I don't have to look at the implementation, it gives me a nice, concise way of looking at the name of the 40 functions I have and what they do. So it's almost like almost self-documenting code. Okay? But as you saw, this online thing uses a more modern compiler, what's called a two-pass compiler. So it goes through your entire program and reads in all the symbols first, then goes through and tries to compile it. So it doesn't require the whole prototyping stuff, but the cool kids prototype or put it in header files, just like the cool kids use direct memory, right? Man, I'm not even down 1 ounce yet. All right. I'm at 46 ounces left. I can do it. Okay. So now I should be able to still print out my array here. I'll go ahead and run this guy. So there's my array, and maybe it's a little bit easier to look at without having the carriage return there, just so you see all of our numbers. Okay, so now we're supposed to write an insertion sort. All right, so we'll go ahead, and this guy is going to return nothing. It'll be void because we're going to update it in memory, right? And we'll call this guy insertion sort. It'll take an int pointer. We'll call it ARN and an int size. Okay, now the way insertion sort works is we start at the bucket 1 of my array. And in each element, we try to move towards the beginning of the array as far as we can until we can't do any more swapping. All right, so I'm going to need a variable for doing my swapping. I'm also going to need a couple of other variables, but let's go ahead and I'm going to create a for loop. We're going to say int curStart. I'm going to say for curStart is equal to 1. Keep going as long as curStart is less than size, curStart plus plus. Okay, so this for loop is going to take a variable curStart on a voyage between 1 and the last legal bucket in my array. All right, now at each of those positions, I want to start from curStart and then move something, bubble something towards the front of the array as far as it will go. All right. So I like to call this variable the follower. Maybe you say it really creepy, like the follower, because the follower follows. That's what he does. So when we do a swap, the follower has to follow that guy towards the front of the array to actually do the swap. So each time through here, we'll say the follower is equal to cur start. So we'll set the follower equal to wherever cur start is. And then we're going to say, as long as the follower is not at bucket 0, which means we don't have a guy before us, and we're supposed to swap. Those two things happen. That is, the guy I'm looking at right now, the guy at position follower, is less than the guy at position follower minus 1. If I'm supposed to swap, then I'll go ahead and do the swap. All right, so we're going to have a while loop. So while follower is not equal to 0. So as long as we're not at the beginning of the list, beginning of the array, which means that I have a guy before me, as long as that's true, and the value at my array plus follower times size of int. This doesn't give me color coding. 1, 2, 3, 2, 1, 0, and that's the end of the while loop, right? 2, 3, 4, 3, 2, 1. Okay. As long as that value is less than, I'm going to steal this here. Follower minus 1 times size of, will this slide over? That's right.
And star, I guess. That is not follow. Before this, there is a arrow mark.
This is less than.
Yeah, no, before that, I think you should start current start.
No. Cur start's going to be follower right here. We're good. All right, so this guy, I just want to make sure I have my parentheses right here. So that's 1, 2, 3, 2, 3, 2, 1, 0. Close it for the while loop. So while follower is not equal to 0 and the value at position follower is less than the value at position follower minus 1. If those two things are true, I need to do a swap. And I'm going to need a temporary variable for doing a swap, so I'll just give myself an int temp right here. So I'll say temp is equal to, I'll go ahead and steal this guy right here, the value that lives at AR at bucket follower. Then I'll overwrite the value that lives at AR at bucket follower with the value that lives at AR at bucket follower minus 1. And then I'll overwrite the value that lives at AR at bucket follower minus 1 with whatever's in temp.
Do you have to have the time size of int?
I think you actually don't in a modern compiler because it knows that it's an integer pointer and it does the right step size. But this is very explicit. So I'm taking integer size steps.
Okay.
So if you didn't do it this way, that's okay because as we've already seen here, things work differently depending on what C compiler you're in. But my intention right now is to be like,
But actually, we are doing a 0, 4, 12, 0, 4, 8, 12. It's
Oh,
not starting at 0, 1, 2 now.
so are you adding 4?
No, I'm saying with this compiler, when you do size of it, it's actually taking, it's not taking array of 0, 1, 2. Now we are doing 0, 4, 8, 12. Because we are doing this into size, in size of int.
Yeah. So size of int should be 4 bytes.
4.
Yeah. So it should be the base address,
Yeah,
then the base address plus 4.
So it internally doing another into 4. Right? What I
Like,
mean?
in other words, you don't need size of int because it's going to
Yeah.
be a 4. It's
Yeah,
gonna
yeah.
be 4. Because if we had numbers that were like bigger, that would take up more than 4 bytes.
No, what I'm saying is now
It's like,
when you do array of 1, it does 1 into size of int. So array of is nothing but array of 0th index plus 4. Internally is doing another size of int.
Right. So you're saying I'm adding too much.
So yeah, it's instead of 4, actually we are accessing 16.
Okay. Well, let's
Yeah.
run it. If it doesn't work, I'll show it in my compiler.
It works, but we are not putting continuously.
I'm not putting continuously.
So 1, 2, 3 index, first index, second index, third index.
Oh, I got it. I'm leaving chunks of my memory open.
Yes.
Okay. What he's saying is I'm not dancing from bucket 0 to bucket 1 to bucket 2 to bucket 3 using the syntax here. I'm actually dancing from bucket 0 to bucket 4 to bucket 8 to bucket 12.
you got a bunch of.
But that's just on here. If I'm on an older, more traditional C compiler, this is saying go to the base address and then take a step. Take this many steps that are the size of an integer.
Gotcha.
Okay? But since this compiler is more modern, saying size of int is actually multiplying my step size. Follower, if I say AR plus follower and follower is 3, I'm already taking 3 integer size steps in this compiler. When I say multiply that by 4, now I'm taking 12 integer size steps.
Which is fine. Both will work just fine.
Well, except that's a little dangerous because I've only allocated enough memory for 50 integers. So that means that if I'm walking off the end of that array and just hoping I'm not breaking stuff out there. Yeah, so this is a little bit deceiving. I like traditional C like this.
Here is a small program. You are not overriding something, but in the real program, you will override some other data.
Yeah, I'll show you, once we have it working, I'll show you a picture of kind of what's going on here. All right, so here's my insertion sort. Follower should follow. So after I do my swaps, that's what that guy is swapping. So after I swap, we'll decrement follower, we'll spin back up as long as follower is not at the beginning, and I should swap, I'll swap. Otherwise, we fall past the end of this for loop, and that should be it. So after I call my print array, I need to go ahead and I need to prototype my insertion sort. So I'll throw that into my funcs.h. And you can take the variable names out if you want. You don't have to. Wrong save button. Okay. So I'll print my array. Then I'll say insertion sort, passing it my array n50. And then I'll print my array again, AR and 50. Save that. Run that. So here's my unsorted array. And then here's my sorted array. That, according to you, I'm using extra memory. 4 times the amount of memory that I needed. Okay? So here, if we want to see that, this will be an interesting.
Print array, just use array of I, and you can test it.
Well, what I can do here is I can print out. We're going to do a print f because we'll see the numbers up there, and we'll say print out the value %d. We'll throw a \n on there, and I want to print the value at AR plus 1. That should be bucket 1, right? And then on the next line, I'll print out AR plus 1 times size of int. All right, so in my world, these should be identical. Okay, you're saying that on here, this is going to give me whatever lived at bucket 1, and this one's going to give me whatever lived at bucket 4. Right, so they'll be different numbers. All right, so let's go ahead and try that here. That's not right. Oh no, it is right. It is right because it. Hold on. I need to do this before my sort. It'll be cleaner that way. Otherwise, I'm seeing small numbers because they're already sorted. All right, so
Yeah, 0 and 12. 0 and 12.
well, I got a 0 and a 32.
There's nothing in 1 percentage.
Well, this should be bucket 0. This should be 1, right? The first thing I'm printing out is the value at AR plus 1, which should be bucket 1 of the array.
Yes.
Oh, but because the way I'm filling the array, I'm filling the array poorly too. Yeah. So what he's saying is this right here. Let me just take that out for a second. Now I'm filling the array in exactly 50 buckets, and then we'll see the difference here. All right, so there's my 32, although that's weird that that's indexed. Oh, my print is still doing the jumps. So there's my 32, but there's my 52.
When I was first writing it, I was getting a bunch of zeros just like that.
Well, it's because we're jumping off the end of the of memory, like he's saying.
Okay.
So if I come in here and I get rid of this guy, I'll have to put those back to show you on my compiler.
Because it's treating those as 4.
It's taking too big of a step. So here's all of my stuff. So bucket 1 is a 32, and bucket 4 is a 52. So
technically you'd only be able
it's showing the difference between AR plus 1 and AR plus 1 times size event. Does that make sense? Now I wonder, can I, will this let me undo in here? No, it won't. So let me take this and copy this into mine. So I'm pretty sure mine takes the...
So technically you'd only be able to put 12 values in there. If it's multiplying times 4. You'd only be able to put 12 values in that, or print out 12 values because it's taking bucket or steps of 4. Is that correct?
Okay. The ID star variable size of it.
Yeah.
I didn't get it.
Oh, okay. I don't know. Maybe I don't know.
Let's do this. I'm going to copy all that. Then I'm going to paste all that.
I don't know.
Oh, I don't have my my funcs thing. I need to grab that. My funcs. Oh, interesting. It does the same thing.
Whatever the compilers I use, they're all basically common.
Yeah, see, I don't like that. I like taking the bigger size steps, like specifying my step size. But that's fine. So I'm still going to generate enough memory to hold 50 of those guys. So I'm still going to hold enough memory for that. But then when I fill it, I'm going to take a step of size 1 or step of size I, not I times size of int, because this guy is actually doing steps of the correct size already.
So wait, when you did multiply times size of int, that was actually taking steps of 4?
Steps of 4.
Okay, that's why I was getting
Yeah.
the zeros. Okay.
Yeah, so it was walking off the, it was your print that was doing it because it was walking off the end of the array.
I was so confused.
All right, so I can get rid of these. So here's my insertion sort. Here's my print array. Get rid of these two guys here. Insertion sort, so now be So I'm going to get rid of the time size event thing there. And I don't have the surround follower with that. I'm going to get rid of the size int there. And this is follower -1. So follower is not equal to 0, and I should swap, then do the swap. And we're going to be swapping AR plus follower. And then again, AR plus follower. And AR plus follower -1. AR follower -1. And print array is already taking the right size steps. I'll just get these parentheses out of here. Okay, so that should sort. So there's our original unsorted, and then there's our sorted version of that. Makes sense? So that's an insertion sort taking the correct size steps through memory. All right, questions about that guy? So I'll go ahead and paste this up on Slack. Yeah, that's weird. All right, and we are 548, right? All right, so there's your insertion sort example. Technically, I didn't put my funcs up there, but that just has my prototyping. Okay. Yep.
What logic you write? Isn't that bubble sort not in?
No, it's pretty close to insertion sort. I gave you a link for insertion sort. Yeah, if you here, let me bring up insertion sort.
Yeah, I was reading there's a couple different ways you can do it.
Yeah, it's what bubble sort sounds like it should be, but it's actually not. So if you go to insertion sort here, you know, they're talking about a couple of variants on this guy. So what it's doing is it goes down the whole list and moves everything up. So it's doing multiple swaps. So here's a graphical example of it. So this is your cur start, and then it's going to keep moving all the way to the front, with bypassing everything rather than doing individual swaps. Cur start's now here. Well, because there's no swap between 8 and 6. But the thing is, you did actually swap. What you just did is they moved this 2 is going to swap with the 8, then swap with the 7, then swap with the 6, then swap with the 5, then swap with the 3, and then it's in its final position here. They're just showing that it moved all the way down here. So you can either implement it by skip the swap and just move it to its final location, and then you have to shift everything else down,
Yeah, that is what happened.
right? But shifting everything else down is the same thing as swapping on the way, because you have to move everything else down in the array after I moved this guy 5 steps up, so now everything else needs to move 5 steps down. So you actually save yourself things by just doing swaps as you go along, individual swaps, because you're doing the same number of instructions. What were you gonna say?
I was just gonna say, moving a whole. Can you do that as a full array? Can you move the whole array down, or do you have to do a loop so that it moves each one down? I was gonna say, like, even if you take it out, then you have to move it.
Yeah.
You have to assign it to a temporary variable.
Well, yeah, you would have, with an array, you would have to move it down, because what you've done is you've freed up a spot here that everything can shift down into. So you would still have to say, this guy moves to here, this guy now moves to here, this guy now moves to here, this guy now moves to here. So you have to,
So you might as well
you're doing the moves anyways. Yeah, so I just do the swaps as I go along. But I agree with you. This looks like we're bubbling the 4 towards the top, right? Feels like it should be called bubble sort, but it's not. Yeah, it's very interesting. Yeah, let's see what this guy says bubble sort looks like. Yeah, see, it's a different algorithm. It makes multiple passes through the data. But you're right. It sounds like it should be bubble sort. Okay. Let's go back. Oh, I have this open. Is that our thing? This is our thing. All right, so that's our insertion sort. Now, I want to look at math with binary numbers here for a little bit. And then we want to look at signed and unsigned numbers. And actually, what we can do for a few minutes here first is let's walk through the instruction set here from the book. I think I can put that in presentation view, yeah, so it looks like this. So earlier, when we, so I think first day of class, we were talking about CPUs, right? And CPUs are kind of a collection of magic tricks. And, we've looked at some assembly language programming and how those magic tricks, how a low-level language translates into exactly one of those magic tricks. So the step we're about to make here, either end of class today or next time, is going to be how do we go from that assembly language to map it to the machine language, turn it into the zeros and ones. But before we do that, we have to have more fun with zeros and ones. But just to kind of flip through here, just to familiarize ourselves with this, so you guys went through these instructions. So they gave you some examples of, so this is an add instruction for an ARM processor. And I think in their thing here, they call it the leg language or something. So it's a subset of the ARM language. So, if we come down here, they have I think a list of things. This, makes maybe more sense. So when you say add x1, x2, x3, that's storing in x1 the value of x2 plus x3. Now, what are all these x's? They're registers. Now, what's a hardware register? When I say hardware register, what am I talking about?
It's the closest to the CPU.
Okay, so it's a little memory chunk.
Yeah.
Okay, and how big are the registers? Little? So 32-bit registers? 64-bit registers? Okay, so we have some word registers and some double word registers. That's probably how the book put it, right? All right. And how many total do we have? How many total registers do we have? 32. So we have X0 to X31. Okay, which ones are 32-bit versus 64-bit? Do they list that in there? It's like the first 16 of them 32-bit registers and the next 16 are 64-bit registers? Or do we have less 64? Do they not talk about that? All right, well, it'll pop up at some other point then. All right, so here's kind of these magic tricks that we run into. So we know how to add two registers together and store the result in a destination register. All right, we know how to subtract, same thing. Now, notice the difference here. We have something called add immediate, ADDI. That's allowing us to take a literal value and add it to the content of an existing register, storing the result in a register. That makes sense? So add immediate allows us to use a regular number as one of our sources rather than a register. Yeah.
What if you were to put a character in
Well, you can't put a character in there.
there? Okay, so it has to
So here, good question. All right, so you stepped off the cliff. Let's.
Sorry.
No, it's what we're talking about today, anyways. Yeah, it's because we need to get really used to working with these binary values because in a computer everything's stored as binaries. As humans, we think of things as characters and strings and all. It's all numbers. Under the hood, the computer's got to store that stuff as numbers, and that's what we really want to investigate in here is how are all those things actually being stored? All right, so when we talk about characters, all right, so you are thinking about something that looks like an A or a B, something like that, right? Okay, now we do have something known as a character set. What's a character set? Or can you tell me the name of a couple of character sets? All right, so we have ASCII and Unicode. All right, so ASCII is the American Standard Set for Instruction Interchange. American Standard Code for Information Interchange. And then Unicode is, so ASCII has 256 unique characters. Let's just put this in here. So this is 256 unique chars. Unicode has 65,536 unique chars. All right, so an ASCII value is actually then stored as some number of bits. How many bits do I need to store 256 unique values? I need 8 bits. So 8 bits. So my smallest 8-bit number is, if we're talking about unsigned numbers right now, we'll talk about signed numbers later today. So this is 000000000. That's my smallest number. This is a 0. My largest number is that. This is 255. Right? Because this is the ones place, the twos place, the fours, the eights, the 16s, the 32s, the 64s, the 128s. So 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 255. All right, so if I want to represent 256 unique values, I need an 8-bit number in order to do that. Make sense? Unicode, though, supports 65,536 unique characters. So somebody other than you. How many bits do I need to represent that? It would be a good exercise for you guys to crunch this anyways. But hopefully after today, this will be pretty common knowledge. Yep, 16. So 2 to the 16th power. So this is, if I have the smallest number here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Largest number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is a 0. This is a 65,535. Trust me. I think my precision will start falling. This is the ones, place, twos, fours, 8s, 16s, 32s, 64s, 128s, 256, 512, 1024, 2048, 4096, 80. Oh, yeah. Yeah, so I'm going to fall off there pretty quick. But trust me, it adds up to that. 65,535. Okay. Another way you can write this is if you say 2 to the 8th power, that gets you your 256 unique characters. 2 to the 16th power gets you your 65,536 unique characters. All right, so if you need to know what bit space you need to represent a value, like if I said you need to represent 131,000 numbers, you might need a 17-bit number, something like that. And these things actually come up pretty often when you talk about things like cryptography. You know, when you talk about security and stuff, and you think about what's the, you know, how big's your key? You know, so if we say encryption, because we're all, at this point, we're talking about data representation and how do computers do it. So if we're talking about encryption, well, if you only had a 4-bit key, that means you have 2 to the 4th possibilities. There's only 16 possible codes. So think about like your what if your door, you have the programming thing for a garage door, have the little buttons on it, but if there's only 2 buttons, 0 and 1, okay, and it was some 4-bit value, you only have to try 16 of those until you definitely are going to get in that garage. Because there's only 16 unique 4-bit values, right? So obviously, if you want to make it more secure, you up the number of bits, right? So you might have a 256-bit key, or you might have a gigabit key, so on and so forth. The more keys, the more bits, the more unique keys.
So if you do 256, it'd be 2 to the 256.
Yeah, 2 to the 256, which seems like a giant number, but it's not an infinite number. And this has actually become a problem in cryptography today, because you might say, okay, if we're going to use the 256-bit key, that's a giant number, right? So if we think about this from an old-fashioned perspective, if I'm just a human being and I need to try 2 to 256-bit unique keys, that would take me many lifetimes, right? Plus, it's a really heavy keychain. Now, computers go way faster than humans do. So how long would it take a computer? So this is called a brute force approach. How long would it take a computer to solve or to try every single one of those keys? Well, our initial thought might be, oh, well, certainly a lot faster, right? Well, now you got to think about, well, how many keys per second can a computer try? Let's just keep the number easy. Let's just say a computer can do 1,000 keys a second. Let's just use that as a value. So if I do 2 to the 256 bits, I divide that by 1,000. So that's the number of seconds I'm going to have to take. All right. So now I'm going to divide that by 60. That's the number of minutes. Okay. Then I'm going to divide that by 60 again to get me the number of hours. Then I'm going to divide that by 24 to get me the number of days. Then I'm going to divide that by 365 to get me the number of years. A lot. A lot of years, right? So that number didn't shrink down as fast as we wanted it to when we were doing the math. So we might say, oh, well, that's plenty secure, right? 256 bits. I mean, unless the computer guesses on the very first key, that's going to take zillions and zillions of years. So is 256 bits secure enough?
Well, wouldn't it be faster than 1,000 a second?
Even if it is. I mean, we got to stretch it pretty far in order for that guy to come down to anything in reality, right?
Now they speak about quantum computers, they can crack this kind of.
Yeah, that's a whole different. But you're right. But our world of computing today is different than this. This is what if one computer is working on this problem? Well, with the internet, we're dealing with distributed computing all over the place, right? So what if we had 100,000 computers, each trying to crack the same code, each trying their own subset of the keys? Now we're going at 100,000 times faster. That makes sense?
Yeah.
And if those computers keep getting faster and faster and they can test more keys per second, all of a sudden something that seemed to be impossibly secure before now is very doable. Yeah, there's an interesting website. I think it's probably still up. I used to mess around on this site a while ago. So it's called distributed.net. Oh, yeah, I haven't even updated the site. Perfect. All right, so you guys have heard of projects like SETI at home, that kind of stuff? Or even, I mean, heck, you could even say the cryptocurrency mining type stuff is the same type of thing. You're going to use your computers to do something else, right? Well, years ago when I was an undergrad, we would use, well, actually, I guess I was in grad school at the time. We would use our computers to try to stress test encryption algorithms. So distributed.net had a client. They probably still have the client. And you would say, okay, I want to try to stress test one of the encryption algorithms, maybe triple DES or something like that, one of the algorithms. And you and a whole bunch of other people, distributed attack on this problem, would see how secure common encryption algorithms were if you had a whole bunch of people trying to hack them, and see how long it would take until you were, by brute force, able to break the code. And I remember it was a very funny thing when this happened. So there was I think this was for triple DES, which was a encryption algorithm made by the government, U.S. government. And they were bragging about how this thing was supposed to be basically unbreakable, blah, 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 just to get the most secure thing ever. Now, what was funny is, so when it came out, Distributed.net was going to stress test this. So the government claimed this was unbreakable. All right. Distribute.net approaches the problem as a distributed problem, so and it's brute force. So it's not like they try to do any funky math stuff. They just try this key, then this key, and this key, then this key until they finally unlock it. How long do you think it took Distributed.net to crack it? Remember, this is the thing the government said was uncrackable.
So 10 minutes.
17 seconds.
No way.
Took like no time whatsoever. And what's really funny is I don't think Distributed.net was first. If I remember correctly, and that's not a guarantee here, some group built a special purpose computer specifically for cracking triple DES. All right, so kind of like with like Bitcoin mining, they make specific circuits for just doing that one math problem. So they built some sort of hardware that only tested triple DES keys. And I think it cracked it like in 2 or 3 seconds or something like that, some very short period of time. As you would imagine, the government was quite embarrassed that their unbreakable algorithm didn't make it a minute. So it's... But just kind of an interesting backstory. But in any case here, so when we were talking about characters, even though humans think about these guys as like A or B, in a computer, we're going to have some way of mapping what we think about A's and B's and C's to an underlying data representation based on bits. And that's where ASCII or Unicode comes in. Now, the first 256 characters of Unicode are the same as ASCII. So Unicode is a superset of ASCII. Because the deal is this. If you look at the ASCII character set, they basically just assumed that the only language worth speaking was English. Okay, now that means that we needed the 26 characters of the alphabet, upper and lower, so we need 52, right? Then you need 0 through 9, so now you're at 62. Then you need your punctuation stuff, right? Commas and question marks and all that stuff. And then you have some other extraneous things. So now we're at maybe 100 and something. So then they started putting things like smiley faces, and they have like some playing card looking things for making games, because they just had filler. You know, they just wasted the rest of the character set for nothing. But I'm not sure if you're aware of this, but did you know that there's languages other than English?
No way.
Yeah, seriously. Okay, I mean, Van back here, he speaks Vietnamese. We got Hindi spoken in here, and Urdu, and Tamil, speaks Tamil. All Telugu, we got Telugu. I mean, so it's all over the place. We just got so many languages that ASCII just wasn't going to cover it. So Unicode covers symbols from not every language. You got some of those African countries that have like clicks and pops and stuff like that, and I don't know. They might not even have written language. I don't know, but it does a way better job of covering the world of languages. But notice that we only needed 16 bits to do that. And from our perspective today, 16 bits is no big deal, right? We've had the discussion that memory used to be really expensive, so an extra 8 bits a long time ago might have been a problem, because that would have maybe been a lot of money to have that extra 8 bits. But now, who cares? We were just talking a few minutes ago with an ARM processor. How many of those 32-bit registers are how many of the 32 registers are 32-bit versus 64-bit? And I don't know the answer to that. We'll stumble upon it because I haven't worked with ARM too much. But the point is, it doesn't matter, right? If at the end of the day they were all 64-bit registers, that would probably be fine, right? My guess is they're not, because they probably need, they probably have a couple of different address spaces for it, and we'll talk about that with high and low space. But the punchline is that that's not really our concern anymore. So in any case, if we're going to, let me just look up, just to keep it simple here, I'm going to look up the ASCII character set. So here's our ASCII table. So this shows you what our character set is. So somewhere in here, where's my A's? So uppercase A is a 65. Uppercase Z is a 90. We have a lowercase is 97 to 122. So that means if I had the char A, capital A, and I tried to print it out, I wanted the integer version of that, it's going to be 65. All right, we can show that in here real quick. So here, let me just gut what I have in main here real quick. So I'm going to say char C is equal to an uppercase A, and then I'll do a printf %d \n, and I'm going to print out the value of C, but as an integer, as a decimal. All right, so this should print out a 65. There's my 65. That makes sense? Yeah. But that's still for human eyes only, because it's not storing a 65. It's storing the binary version of 65, right? Which is going to be a 1 in the 64's place. So it needs a, well, if we're using Unicode, it's going to be a 16-bit space to represent that value. So if we look at that 65.
So essentially every letter that you put in there is translated to binary instantly.
Correct. So A, capital A, is number 65 decimal in the character set. I'm just going to go ahead and, so this is going to be a 1 in the 64's place, a 0 in the 32, 0 in the 16, 8, 4, 2, 1. So that should be a 65. And that's, how many bits do I have? 1, 2, 3, 4, 5, 6, 7. 7, 8. 9, 10, 11, 12, 13, 14, 15, 16. So that is the Unicode value for an A. A whole bunch of zeros followed by a 1 in the 64's place and a 1 in the 1's place. Gives you a 65. So under the hood, the character uppercase A is stored like this. All right. But using an assembly language, like the ARM assembly language, the leg language that they're showing us here. If I wanted to store a capital A, for example, this guy. So here's some things down here to, I can load something into a register. Let's store a word. That's storing it at some memory. I'm going to load. If these guys are 32, if we assume this is 32, and we're going to only load 16 in, so I can load into the high memory. It says load half. So actually, it's probably loading low. So this is loading into the first 16 bits, assuming this guy is a 32-bit register. So I'm going to store into the low part of X1 the value that lives at X2 offset 40. So we would have had to put some stuff into the memory there. If we want to cheat this a little bit, we can do something like, we still have to load an initial value in. So let me see what their thing is here. Those are our jumps. So that's a byte stored in memory. Here I can store an entire, I can load a register. Yeah, you'd probably use this one. You'd probably say load into X1, and then you'd have to give it the value that's in X2. So how do we get the initial value in there? They give me an example of this. Let me just see if they show me an example, and I'll tell you how it works. They just blankly say, oh, those values are already in those registers.
Just move MOV.
Do they have a move?
They have MOV from K and
I didn't see it in that list.
MOVZ they have. But this is a constant.
Oh, yeah, that's fine. That's what we want. Yeah, we'd use this, move Z. So this loads a 16-bit constant and pads the rest with zeros like I just did in that last example. So we would move into X1 a 65 as a human, right? And that would load it up with what we just wrote here, those 16 bits. That's what would end up getting stored in that register, a bunch of bits, even though we said 65. I moved into X1 a 65, so if we do, so we would say something like move Z X1 65. So that would move into X1 the binary equivalent of 65, padded out with zeros. If we needed zeros in there, as opposed to it looked like there was a second one here that left the rest unchanged. So if I already had stuff in X1 and I went to overwrite it and I used the move K, it would only overwrite as much of the bits as it needed. It would leave the other bits alone.
So it changed the value.
Where you would have a fairly random value unless you knew what was previously there. Like there might be a reason why you would do that just because of the nature of the value that used to be there and what you were doing to it. Okay, but if you were just saying, look, I'm just storing some new stuff there, and I don't want any of my old stuff to corrupt it, you're going to store it with zeros padding.
Like if you knew there was just a 1 at the beginning of that, and that represented a really big number, and you want to save memory, is that why you override it like with the K? With the K?
Not necessarily. I think you could potentially do that, especially if you're looking at the high or the low portion of a 32-bit register. Like you probably could fake it and get a 16-bit value in the low and a 16-bit value in the high. But I would think it would make more sense when, maybe it would be when you want to save some memory, which I don't know that you would think about too much, but keep in mind that ARM processors are mostly immobile, so you probably do pay more attention to memory there than you do in your PCs, but still we don't pay tons of attention to memory. But if you're only going to load something, but then you'd have to, when you go and get it, when you get something out of it, you're going to have to use this offset thing to make sure you're only touching the bits that are relative to what you need. So this is kind of like what we've been writing. Here's a base address, and here's the offset from that base address. Kind of like we've been doing in C.
Yeah.
AR plus 4,
Okay. Yeah,
something like that. Yeah, so X2 would hold some address, and then plus 40 would be some number of, I'm assuming that's bits off of that.
Most of these are 32-bit register.
Yeah, so byte from register to memory. No, so just because it's 32-bit, so X2 might hold a memory address like 2000.
Okay.
So then 2000 plus 40 would be 2040. That's the new memory address.
Oh, okay.
Because you're actually storing up, because you have physical system memory on your computer. That's giant. And then you're storing in this register the base address of some place in physical
That's not
memory.
The actual value, it's like the pointer of it.
That's it.
Okay.
Exactly. Okay. So if we wanted to store a character, we would just move the numeric version of that character in here. And then when we went to write the thing that actually displayed something to the screen or did something with that character, built a string, something like that, we would then look it up on the ASCII character set, which is typically built into the CPUs. They have a lookup table for those. Or they have the Unicode character set built in. That way everything is stored as binary. But when you actually go and use it at runtime, part of that conversion would happen as part of that magic trick of getting a character out of that. It might actually be not even at the CPU, it would be at the operating system that would store the character set. So when you told we looked at the example of calling syswrite for Linux, where we would tell it to, here's what I want to write. I want to write this 65, but I want to write it as a string. So depending on what your language is, it might be like a $sign thing for strings. And then it will convert that to its Unicode equivalent and give you the character representation of that. So that's happening at the operating system level. Okay, so whole bunch of things that they've given us here, just a shorthand version, and we'll look at examples as we kind of go through. And but the generalistic stuff is up here. Here's mathy stuff. Here is getting stuff in and out of registers. Here is our logical Boolean type stuff, so ands and ors, and then we also have this thing called shift left and shift right, and we'll look at those. Then down here we have branches. This is the way that your if statements are implemented in assembly code. So we can compare something to a 0, and we can branch conditionally based on something. Or we could also just jump. This is kind of equivalent to a goto in an older language. So this is a cut down version of ARM, but you basically see our goto, our magic tricks, our mathy stuff, storing stuff in registers, doing Boolean stuff that we're going to need for our conditionals, and then conditionals. So kind of our primitives from normal programming, right? Just in little tiny bits. Okay. All right, so as I mentioned before, double words are 64 bits. Right, now you have not looked at 2.3 yet, right? You read through 2.2? All right, so they've represented this thing called the leg V8 architecture. So we have something called words and double words. A word is 32 bits, a double word is 64 bits. I'm not going to worry about this stuff here for a few minutes. This is stuff we're already kind of familiar with. Base addresses versus an offset. We've been messing around with that in C. All right, so for example, if we look at some of this code, we're going to, they show you what this memory looks like. So at X20, they have a 60. At X21, they have a 35. At X22, they have a 5,000. They didn't show you how they got those values in there, but they're in there. So then we're going to load into X9 the value of X22, offset by, this is probably 8 bytes. So no, probably 8 bits. So then you're gonna, so this is a memory address, right? So I mentioned a little bit ago about we have system memory. So now we got to go back to our picture of how our computer is organized. So somewhere in here I had a picture that well, let's just draw one here. So if we think about our computer, we have our system memory. So that's this guy up here. Then we have our CPU. Okay, and we're thinking about ARM stuff. We're thinking about the CPU. And the CPU is surrounded by little registers. I'll just put a couple of them in there. So there's 2 little registers. There's actually 32 of those, right? 32 of those little registers. So when we're going to store in one of these registers some memory address, that is our way of mapping logic that's in the CPU to this resource that's up here. So when you have your system memory, you have your 8 gigs or 16 gigs of RAM. That's large and slower storage, but we can put a lot of crap up there, right? You can fit a lot of stuff up there. So when you need to go and retrieve something from system memory, if it doesn't need to be super, super, super fast and tiny storage like we have in the registers, and we need something in system memory so we can go and grab at it and bring it back in, we might put our data in system memory. So that's loading things into RAM. And then we might store where it lives in there inside of a register. And possibly if you're going to store several things like we've been thinking about arrays, you might deal with it based on an offset of that. So in this example here, here's their picture of system RAM. All right. And they've thrown in here that memory address 508, they've left the rest of system RAM empty. But at memory address 508, they have a 25. Okay. So they're going to say we're going to load into X9 the value that lives at the base address, which is an X22, so that's base address 5,000, plus 8, which would be 5,008. So now we'll go into memory. Here's 5,008. There's our 25. So 25 will get stored inside of X9. That make sense? And then we'll add X21 and X9. So X21 is 35. So that's 60, right? Plus X9, that's 60. And store the result back in X20. So we're adding 2 registers together, storing the result back into another register. So there's why X20 has a 60 in it. Make sense how that's working?
The 5,000, that represents what again?
Of the base address of
Okay.
of this value. So it looks like they have they decided to represent a array called A. They might say that it's an array up here somewhere, but this is very similar to what we've been doing in C. So we have an array here. It looks like this is an array with 100. It's a 640 bit array, right? Because we have 100 double words. Each double word is 64 bits. So, no, 6400 bit array. The base address of this guy is in 5,000. So this is similar to when we come out here in C, and I do something like int pointer A is equal to malloc 100 times size of int or something like that. Let's just leave it at that. All right, this guy's going to give me a memory address. I'm storing that base address in A. All right, and then in assembly code, when we compile this, because that's ultimately how we get assembly code, and we'll talk about that after our break. When we compile this, somewhere we need to store in a register where A starts. So presumably they've loaded into a register x22 the base address of A. So they've moved into x22, move Z into x22 5000, which is the base address in memory of where A lived. And then from there, we can operate off that base address and an offset to get us bucket 8 of that array, which lives right here in position 5008. And that gets me the 25. That's the only value they've shown me in there, but presumably they have a whole bunch of other values.
And you said each register would have up to 6400.
This register, each of these registers have up to 64 bits. I don't know the breakdown between 32-bit ones and 64-bit ones, but we can assume for our thinking right now that every register is 64 bits. But that doesn't necessarily mean that that's the size of these. So these are bytes in memory. So this is byte 5000, byte 5001, 5002. So I'm going to an offset. I'm going to the base address 5000, and I'm offsetting 8 bytes to get to memory address 5008, and I'm finding the guy that lives there. That make sense?
Oh, gotcha, because we're reading from memory.
Yeah. That's where we have the disconnect. So this is system RAM. This is the CPU and registers. So these guys are the super fast stuff. These guys are a little bit slower stuff, but a lot more storage space. But I mean, this is an important concept because this really is often confused. Because the second, I've mentioned this before with pointers, the second we start talking about memory, we start getting intimidated because memory is scary. So now we're talking about different kinds of memory. We got this gigantic system memory that has a whole bunch of space in it. And that's where we'll put stuff that, might be bigger if we need to store 1,000 numbers. Okay, well, we only got 32 registers. Okay, we have 32 registers. We can't store 1,000 numbers. So instead, we're going to have to put our numbers up in system RAM where we have plenty of space and then store in one of our registers where we can find those values. That makes sense? Now we're only using one register to get to our 1,000 values. All right, so at the cost of speed. If I had 1,000 registers, I could access those 1,000 values really fast. But now I can't. I have to go to super slow system memory. At least it's not on the hard drive. That'd be even slower. But in this world, we usually think of system RAM as being very fast, but in the world of the CPU, compared to a register, system RAM is incredibly slow. Okay, let's take about a 10-minute break, and we'll come back, and we'll finish looking through this, and I want to start looking at 2's complement stuff.